So, hi everyone. I am Anuj Kumar, working as a Prime Minister Research Fellow at IIT Roorkee, and I'm the TA for this course, which is entitled as Trace and Ultra Trace Analysis of Metals using AAS. Okay, so I will be today I will be discussing assignment 7 for this course. Okay, let me. Uh, okay, fine. So this is the assignment 7, and the first question is related to the flame AES and flame AAS. The main difference between the instrumentation from flame atomic emission spectroscopy and atomic absorption spectroscopy is you are given four options. First is prism is used for dispersion, simple instrument, low cost, and fourth one is the source of light is not required. Okay, so you have to select the appropriate answer. It is very easy question. You know, in AES there is no source of light required. You just directly atomize the sample and note the readings, right? So, like if I describe the basic components of the flame spectrometers, they include first is the sample delivery system, second is flame, which is the excitation and emission media, third is the optics that is needed to isolate the desired spectral lines. Okay, fourth is the detector, and last one is the recorder, right? So you can see here the optical diagram of flame photometer, right? So there is one atomizer and two oxidant and fuel gas are there. So this is the flame, okay, and you will be putting a prism, that is basically a prism analyzer that will disperse the the radiations coming out from the flame, right? After that, the variable slit with which will choose the specific wavelength, and in the photocell this radiation will fall out on the anode of the photocell that will convert basically the radiation into the current, and amplifier will amplify it, and finally detector will detect the signal, right? So there you can see there is no light source required here. Okay, so reflector is basically what is the function of reflector here? If some radiation is going there, okay, so that can reflect the radiation into the appropriate side, so that uh, spectra may also be collected, right? So the basic difference between the instrumentation of both the techniques is there is no source of light required in the flame emission spectroscopy. But in the AAS, there are various types of light source you require, basically hollow cathode lamp, okay, and electrodeless discharge lamp EDL. Okay, you have already read about that. Clear? So the next question, the four elements are given here: strontium, silver, zinc, and lead. Okay, so you have to determine that which element is will be determined by flame AES, because you know atomic emission spectroscopy can determine some specific elements, right? So you have to select basically among these options. Okay, so I'll wait for 1 or 2 minutes, and after that I'll explain. So in the introduction section, you have, I think you have read about the atomic emission spectroscopy. It can efficiently determine the alkali metals alkali metals and alkali earth metals, right? So now your work is very easy. You have to basically select which is the alkali or alkaline earth metals among these. Okay, right. So these are general applications for from flame photometry. That is, first it can qualitatively and quantitatively analyze the alkali and alkaline earth metals. Okay, nowadays, it is extensively applied for the determination of sodium, potassium, lithium, calcium, magnesium, and strontium in the analysis of water. Basically, there are different matrices, matrix, glass, biological samples, petroleum products, cement, metallurgical samples, etc. Okay, so this is a typical range, right? For which it works basically. I'm telling the linear about the range that is 1 to 50 ppm. Okay, you can determine as low as 1 ppm of the metal ions and determine up to 50 ppm. This is a typically analysis range. Otherwise, it depends upon the type of analyte, specifically if I talk about, right? So this strontium will be the right answer. Okay, because you can see the barium, magnesium, calcium, like that, right? Okay, so the typical concentration range for flame photometry is, I have already told about 1 to 50 ppm, right? So you have to remember the concentration range for flame photometry, right? Basically, flame photometry is a very cost-effective technique, but it has some limitation that it can be applied only for alkali and alkaline earth metals, right? Also, it is an absolute technique. Absolute means you don't need to record the response relatively, right? Okay. The main reason for using non-flame AES. This question is basically talking about the techniques in which we don't use a flame. That is a non-flame AAS. So what is the main reason, or you can say the advantage for using non-flame AAS? They offer low detection limits. They show high reproducibility. They show high accuracy. Okay, or they are very easy uh, in the analysis, right? They are easy to operate. Okay, so atomic absorption analysis using flame atomization. So uh, atomic absorption analysis using flame atomization presupposes that the sample is in solution. Okay, for the analysis of solids in ppm level, bringing the sample in solution itself improves involves the dilution, right? If you are dissolving any solid into a liquid, it is basically a dilution of solid sample, right? So that the concentration of the analyte in ppm will become a small fraction of the original content, right? So thus the limit of detection for a particular element is directly proportional to the concentration of atoms in the flame, which is further dependent on the flow rate of solution, efficiency of nebulization and atomization efficiency. This whole details is about a flame AAS. Since the flow rate of the gases is always high, the time spent by the free atoms in the flame is very short, or it is of the order of 10 raised to minus 4 seconds, right? So increase of free atoms by higher intake of sample is restricted by the burner design and moreover causes a deterioration of flame stability. Okay, so people thought all these factors tend to limit the atomic concentration in the flame, right? Basically, there are some limitation that a limits the atomic concentration in the flame. Okay, so that's why the detection limit is also compromised. Okay, or it may reduce the sensitivity also. Therefore, when the sample size is very small, let's say 5 to 10 microliter, it is necessary to work at the absolute detection limit. Okay, so you have only 5 to 10 microliter, 1000 microliter is 1 ml. So 5 to 10 microliter sample like blood, tissue, brain sample, etc. If you get, it is necessary to work at the absolute detection limits. Okay, and which is expressed in micrograms. So therefore, non-flame atomization methods have been investigated. So after reading all these statements, what you can guess? So the non-flame techniques are only used for reducing the detection limit, right? So the non-flame AAS is basically a absolute technique, right? So it offers the low detection limit. So that is the main advantage for this, right? And detection limit in nowadays are playing a very crucial role in the analysis. Basically, some instruments are designed in a way that they can offer a lower detection limit as compared to the existing version, right? In the like you can say in the MS mass spectroscopy, every year there is a new development for improving the LOD only, right? Or and not LOD. There can be many other objectives also. Okay, so that is a matter of a different way. So the next question is the graphite AAS related. So the pyrolytic graphite coating on graphite surface is done. So why we need a pyrolytic graphite coating on graphite surface? Okay, to reduce the permeability and enhance the performance of the graphite tube. Second is to increase the hardness. Third is to prevent oxidation, and fourth is to enhance the life of the tube. Okay, so in the lectures you have already read about it that the graphite, if there is a graphite tube and it is not pyrolytic, okay, that it contains spores, so the metals can permeate from the graphite tube. Okay, so let me discuss into details. So these are some graphite tube characteristics. Okay, uh, in the instrument configurations that we need a graphite tube as long as possible because we want the free atoms to remain for longer time in that tube for better analysis. Okay, so that can affect the sensitivity also, right? So apart from the good geometry, the tube material and surface characteristics are very crucial. Okay, in electrothermal AAS. So it is well known that high temperature graphite surface is highly permeable to metal atoms. Okay, so to prevent this permeability of the graphite surface at high temperature, okay, so first the people thought why not we use tubes made of tantalum, molybdenum, tungsten. Okay, so what they do, they first fill the graphite tube with a tungsten salt, tantalum salt, and molybdenum salt for closing the pores, and then put their sample. But this is the one way of doing it, and this resulted in better sensitivity and reproducibility. But in graphite furnace, whenever we are doing atomic absorption, sensitivity and reproducibility is very important factor. Okay, so every time you do this operation, you should get the same reading now, and that is something to do with the precision and accuracy that is required in every technique, right? So how we solve the problem of the permeability? Okay, so what we do, we attributed the sealing of the cracks and defects in the furnace because graphite tube is surface basically, and they thought that whatever is permeable material, if I put some amount of tantalum side, it will close these pores, and then they know more permeation is possible. So Alvo found that tubes made of pyrolytic graphite had the same properties. Okay, so you can see the figure of pyrolytic graphite. There are no pores, right? One is upper layer, and the pores of first layer is filled by the second layer of the graphene, right? So this all design is basically done for the to prevent the permeability of metals from the graphite surface. So first will be the right answer. So the preferred gas used in graphite furnace AAS, that is AAS, is nitrogen, hydrogen, argon, or helium. You know, this is the argon. So what are the system consideration? If I talk about the electrothermal AAS, it is important to use argon. Why? Because it is inert. It prevents metal atoms reacting with atmospheric oxygen to form refractory oxides, which are very resistant to heat and interfere in the analysis. It physically transports the matrix component out of the radiation beam before atomization, thus eliminate much of the background radiation. Because in the configuration you have read, this is basically there is a this type of this is a sample, and the argon flux is continuously running there, so that transport the matrix components out of the radiation beam before atomization, right? Or you easily can control the flow of purge gas. Argon is basically a purge gas. Okay, or you can reduce it to zero during measurement to obtain better sensitivity, right? So these are four system considerations, or you can say the advantage of using argon gas in this technique. So next one is related to the heating steps. The heating steps in GFAAS are chosen such that all the materials more volatile than the analyte are removed before atomization step, right? Solvent is removed, compounds are decomposed, or the compounds are ignited, right? Basically, we do the programming, heating program, such that all the interfering, or you can say matrix components are volatilized, so that they should not interfere with the atom, right? This is the temperature control technique, and in electrothermal AAS it is possible to heat the tube and hence the sample at a controlled rate in a series of stepwise increments, right? Like here, first you put 90 degrees you put the tube at 90 degrees centigrade for 1 second, then ramp it. Ramp means you provide the heating rate, just like 2 degrees second per second, 2 degrees centigrade per second. Okay, and increases up to 120 degrees Celsius and hold there for 10 seconds, right? So at 120 degrees Celsius, the water will be removed, not completely, right? So, similarly, other temperature programs may be incorporated to remove organic matter, inorganic salts, until all the contaminants are removed and only metallic elements are left, right? So, for the atomization, a maximum heating rate is selected to obtain best sensitivity. All such pretreatments may be standardized in the preliminary experiment before optimizing the temperature program, right? So, all the materials more volatile than analyte are removed before atomization step, because if you evaporate all the materials other than the analyte during the atomization step, you will get only the atoms that that is basically needed only, right? So that is basically the purpose of the heating steps in this. So programming temperature is used for that purpose, right? So the first one will be the right answer for this. Next is related to the matrix modifier. So, which chemical is used as a matrix modifier in uh, this technique, electrothermal AAS, right? Sodium chloride and ammonium nitrate, or sodium phosphate. There are many matrix modifier, okay, but most commonly used is ammonium nitrate. What it basically do, it converts NaCl, it reacts with NaCl and convert into sodium nitrate and ammonium chloride. So these both reaction products can be easily decomposed or sublimed around 400 degrees Celsius. Okay, so the interference is basically reduced at this temperature. If the analyte element is also volatile, a low temperature atomization must be considered, even though it leads to lower sensitivity. But the matrix component would not volatilize. So thus cadmium can be determined in the presence of 2% NaCl at 750 degrees Celsius, where NaCl do not volatilize. When the volatilities of the matrix and analytes are similar, their thermal pretreatment alone cannot guarantee the satisfactory separation of the element. Okay, so in such cases, phosphoric acid and nitric acid may be employed as acing additive for biological and organic samples. Right. There are several others matrix modifier also, right? In like lanthanum for lead, phosphoric acid for cadmium, calcium nitrate for magnesium, potassium dichromate for mercury, and magnesium nitrate for manganese, all aluminium, chromium, cobalt, nickel, etc. Okay, so apart from increasing the stabilization temperature to 1200 to 1400 degrees Celsius, numerous interferences are also eliminated when these modifiers are used. Okay, so this is the right answer. So in the graphite furnace AAS, ionization is low. Why? Because temperatures are high, temperatures are low, concentration of free electrons is high, or the fourth one is argon is present. Why ionization is low? Okay, so this is related to vapor phase interferences. In graphite furnace, just like flame, dissociation and ionization take place according to the law of mass action. Okay, so however, owing to high concentration of free electrons, ionization is quite slow, right? In the previous lecture, I have discussed about let's say Taylor principle, in which if you add the same element in excess, the equilibrium is shifted towards the metal. That is basically the preventing of ionization. Okay, so in graphite furnace there are a very high concentration of free electrons that basically uh, slows the ionization process. So this one is the right answer. The next one is the related to the interference regarding sodium sulfate. Sodium sulfate hinders atomization of many elements due to precipitation, the presence of oxygen, presence of sulfur, or molecular absorption. Okay, I'll wait for 2 minutes and after that I'll explain. So, if I discuss about the presence of sodium sulfate, it basically hinders the quantitative atomization of a number of elements. This is due to the presence of oxygen. Okay. Further proof is obtained when oxygen is mixed with the purge gas, which also produces smaller number of atoms, and a smaller signal is observed, and which is which appears uh, at very higher time, or it can you can say the delayed appearance is there. Okay. Similarly, excess nitrate in a sample also leads to the error when compared with the nitrate-free reference solutions. So salts easiest to decompose, decrease the signal, whereas other enhances the signal. This is quite important because even the simplest samples contain nitrates, right? So sodium sulfate indulges the quantitative atomization of a number of elements. This is due to the presence of oxygen, right? Why? Because some oxides are very stable, or molecular absorption can also be a reason for this, right? So next question is numerical type problem. You are given the ratios of excited potassium atoms to the ground state. Okay, that is Nj by N naught. It is 4.58 into 10 raised to minus 4, right? You have to calculate the corresponding temperature in Kelvin. And given the statistical weights for 3s and 3p state being 2 and 6, right? So 3s and 3p. So G for this is 2 and G is 6, right? So this is the excited state. Okay. So Gj will be 6 and G0 will be 2. And the energy of excitation is delta E is 2.59 into 10 raised to minus 19 joule. Okay. So let me insert a blank slide here. Okay. So you have to apply this formula here. Nj by N naught is equal to Gj by G naught e to the power minus delta E by kT. Okay. So Nj by N naught is 4.58 into 10 raised to minus 4, and if I put the value 6 by 2 e to power minus energy value is given here 2.59 into 10 raised to power minus 19 divided by K is 1.38 10 raised to minus 23, and temperature is T. Okay. So you have to do some mathematical calculations. Let me do also. Okay. So it will be a 4.58 10 raised to minus 4 and divide by 3, right? And e to the power minus 2.59 divided by 1.38, that is 1.87, sorry, 10 raised to 4 divided by t, right? And if I write like this, sorry, 1.87 10 raised to power 4 divided by t is equal to ln 1.58 divided by 3, that is 1.52 into 10 raised to minus 4. Okay, and you can convert minus 87 10 raised to power 4 by t equal to 2.303. It will be log 1.52 into 10 raised to minus 4, right? So what will be the value of this term? You will be getting the answer for t. Okay, so let me do 1.52. This is 2.303. Log 1.52 will be 0.181, and it will be minus 4, right? So 4 minus 0.18, that will be minus 8.79, something like that. Okay, so you will be getting 1.87 10 raised to power 4 divided by 8.79 equal to t, right? 1.87, that will be 0.2127 into 10 raised to 4, or you can write 2127 Kelvin, right? So the right answer will be 2127 Kelvin. Okay, so this question was related to the population in higher states and ground states, and using this expression you have to basically find out the value of temperature T, right? So this was all about session assignment 7. Thanks for attending this session. I'll meet you in the assignment 8. Thanks a lot.